Hello, everyone. This is our Group 1 design presentation. My name is Thomas.
Hi, my name is Sarah.
Howdy, I'm Dawson.
Howdy, my name is Mishika, and I'm going to be continuing the presentation. So what the hemostasis valve does is it allows for irrigation of guide wires and catheters to help prevent thromboembolism or other complications. The current hemostasis valve relies on either the Toy-Vorst valves or other saline inflation seals. In our research process, we also looked at the valve made by Gore Medical. Our need statements are as follows. A patient undergoing brain surgery needs to have assurance of safety and prevention of thromboembolism during surgery in order to live a healthier, complication-free life. A doctor performing the surgery under high stress conditions needs to feel confident in the equipment's performance and feel comfortable using the valve so that their workflow is not disrupted and they can carry out the surgery successfully. This table shows how we use our user needs to translate them into design inputs. So in order to attempt to minimize cost for more accessible use, the needs need to be able to have a cheaper production cost. To fit the required guide wires, a 0.035 inch guide wire insertion slit on the top. To fit the required catheters, the catheter insertion point size to 24 French. To prioritize patient safety and comfort to ensure it improves their lives, the design is precision made with an O-ring, which, when fully inflated, prevents any unwanted flow. To form an airtight seal to reduce the risk of air embolism, the rubber material of the inflated valve will have the right amount of pressure to maintain the seal. To reduce the risk of infection during use, the valve will be made out of an antimicrobial material. To enhance the speed and ease of operation for doctors, clear instructions and a demonstration video will be created.
This is the plot matrix we have made for the design. We identified several characteristics of their homostatic valve and compare with three different typical design. The efficiency of the forming a shell, simplicity of use for the daughter, cost and to implement, and the times to implement, and the risk to the patient, and the flexibility and the risk of breaking and manufacturing. After evaluating all the characteristics of the device, we conclude the inflated valve is the best option. So we design our device using this implementation.
So in our research, when we looked at other valves that were on the market, we had the Borscht valve, which included a twisting mechanism that would enclose a rubber seal. We decided that wasn't good because it took a lot of time for the doctor, blood loss while it's being resealed. So we decided to go with more of an inflatable seal perspective. But in our research, we discovered that doctors would have to take an extra step before their surgeries to get a syringe, fill it up with the proper amount of saline, and then inject it to inflate this O-ring to make sure it has the proper amount of pressure. Since we had some concerns that without the right amount of pressure, the valve would not be able to form a proper seal, which could cause a host of unwanted, very, very damaging consequences. So we decided with our valve, we were going to have a pre-filled saline cartridge. Now the saline cartridge, as you can see by the cross section, it has a spring-loaded mechanism that once the doctor pushes two simple buttons on the side, it will push a plate forward that will inject a pre-filled, pre-measured amount of saline into this O-ring, therefore ensuring that it has the perfect amount of saline every time. This means we don't risk not enough pressure with underfilling and too much pressure with overfilling. Another great feature about our valve is that it can accommodate for multiple different sizes of catheters or guide wires. We have this slit at the top where smaller guide wires can be inserted, and we also are able to accommodate on the side for larger 24 up to 24 French catheters.
So next, we've got the DFMEA matrix, in which we identified risks and other characteristics associated with them, including their effects, causes, occurrence, and summed them up into the risk prevention number, where a higher RPN is significant and shows that the risk is to be avoided at all costs. So while there's a lot on here, there's a few main risks that we looked at along with actions taken. The first one was that the valve does not properly reseal, which would cause profuse blood loss and could be caused by manufacturing defects or damage in transit. So to avoid this, we have an extra focus on quality control for the balloon material, causing a leak. To prevent this, we decided to control the amount of saline allowed to enter the seal with a pre-filled cartridge, like Sarah mentioned in the previous slide. The third major risk we looked at is that the device is too cumbersome for doctors to get used to. And to avoid this, we provide a demonstration video and a clear instruction pamphlet sold with the product. Next, we have our risk matrix, in which we identified risks, gave them a scale based on their impact and their likelihood, and placed them on this chart, color-coded to show the more severe risks. The most severe risks that occur is that the device is slow for doctors to adjust to, or that a non-tight seal forms, causing from incomplete inflation, both of which have a 10 out of 25. One of them occurs very frequently, but has a minor chance or a minor impact to the patient, whereas the other one occurs very rarely, but has a more severe impact. In addition, on this chart, we've placed an overinflated seal, transfer of bacteria, a pierced inflatable device, and the catheter not fitting, with small risks with this device, but not very many that are both severe and likely, indicating that we did a good job with our design to avoid risks. So in conclusion, our design accomplishes the goals of faster use and reduces the risk of user error. It places the burden on precise procedures when creating the product rather than on proper use for the doctors. And altogether, this is an improvement on the current hemostasis valves without being too disruptive to doctors and their routines. And then here are the two main references we used when we were reading up about current engineering methods in the valve market.